Well, first, again, thanks, Anna, for the invitation to give this summary talk. Of course, it's an honor. It's also a lot of work. And the idea when I put it together was to try to make a, of course, personal point of view of a coherent way of presenting all of the ideas that have been discussed here during this workshop. And because of that, of course, being a personal perspective, it may be, of course, incomplete. I confess that I am not an expert in many of these areas, but I've tried to do my best. And of course, I apologize beforehand if I did not give enough highlight or credit to the work that was presented. So, but I believe that perhaps the main point of this summary will be at the end to try to motivate a small discussion and perspectives for what we do and how we can well, move forward in these very interesting subjects. So with that said, what I'll do is to flash what were, according to this perspective, some of the highlights of the, what is the order of the or what were the subjects that were touched upon and discussed. And so let me start with this one, which was discussed by William, Ricardo, Norberto, and Luis. Well, perhaps not so much by Luis, but I put it here because it has to do with the way we think that vacuum has to be regularized, and in particular for the calculation of what the meson masses are in the presence of a magnetic field. So William showed that you need to be careful when regularizing with a prescription, in particular in some models where you sometimes have entangled the effects of vacuum and in this case, thermomagnetic effects. And so if you separate vacuum, then you get some smoother curves and something closer to what lattice calculation shows. And of course, it works not all the times, but sometimes it's not possible to do that. And Ricardo discussed with us that in the case of when you introduce an anomalous magnetic moment, then perhaps this term is important, and so he kept it. And he also discussed about the way we should compute this renormalized magnetization. So another important aspect that was touched upon in this section was given by Norberto. And what he emphasized, and it's still intriguing to me, but I believe that it may have also some clues, is that when you want to study the masses of bosons, particular neutral bosons, you have to be careful and remember that there may be mixing. And so mixing seems to be important, and this can help us to understand the behavior in magnetized matter of the trend of neutral bosons as a function of the magnetic field. Luis, he also emphasized that it was important to relate the way NGL, together with the random phase approximation, computes the meson masses. And so he did full dressing of all of the magnetic field effects, and with model, of course, modeling this with the linear sigma model, he found that he is not able to reproduce the behavior shown by lattice calculations, in this case, for the screening masses. So here you can already see a connection, a possible connection. In other words, if mixing is important, and mixing is not present in this model, so perhaps some cross-talking here could be interesting. Now, let me move forward to the other subject, which I chose to unify the information that was conveyed. And I call this the theory developments. And here I put Marcelo's, Christian's, Maria, Tulio, Alfonso, Kenji, Enrique, Jorge, and Saul's contributions. And so let me mention that there was an interesting subject here that emphasized that you can follow the deconfinement transition if you look at pure Yang-Mills theories, and if you work in the background gauge methods. And so if you introduce in this effective action description a gluon mass, then you can see that there is a clear indication of a deconfinement transition by the peak of the two particle correlation function. Christian studied the magnetic field effects together, or perhaps more importantly, for the deconfinement parameter in the finite energy sum rules. And so he showed that for the pure magnetic field effect, this parameter always grows, and so it indicates clearly that there is magnetic catalysis. So this is the behavior that he showed. Marcelo reminded us that, well, he started by reminding us that there is also interesting effects that can be studied in the case of heavy ion collisions, but for non-symmetric systems. So if you look at these kind of collisions, then you can produce electric fields that then suffer the inverse electric catalysis phenomenon as well. So the analysis was done in a toy model, but still it may reveal some interesting features of these systems. Then Tulio discussed what was the behavior of the QCD pressure at finite temperature and high magnetic field intensities. Interestingly enough, what he wants was to study the behavior of the pressure as a function of the masses of the particles in the game, and the important one, of course, is the strange quark, because in this case, this is a heavier one, and so he needed the thermomagnetic behavior of the quark mass, of the strange quark mass. And so he put it into the game, and then he concludes that in order to check whether these ideas make sense, it'll be great that lattice QCD, the lattice QCD community could compute this pressure. Then Alfonso was looking at this more theoretical problem in which he studied the magnetized plasma in these ideas of duality. And so he showed that his model can reproduce qualitatively the behavior of the pressure as a function of the two kinds of pressures as a function of the magnetic field. Kenji, of course, did a very large review. I think that I'm not going to be able to make to be able to convey to you most of the information that he asked or he gave us. But the important discussion is that for what he called the inhomogeneous presence of a magnetic field, you can see that there is a magnetic field aided confinement. So he illustrated this by looking at how the pressure distribution changes when you change the field intensity as a function of the distance. And then Enrique showed us this morning that that fermions in a magnetic field not only have mass, and that mass can be extracted as the pole of the propagator, fermion propagator, but it also has, or they can also develop an imaginary part. And because of that, this function, this spectral distribution develops a sort of a Lorentzian kind of shape. And so you can see that the distribution has a width, and is given by this imaginary part of the fermion propagator. And of course, it depends on the magnetic field, and as the magnetic field grows, this approaches more and more as a delta function. Then Jorge also this morning discussed about how you could perhaps imagine that in an environment with a lot of gluons and magnetic fields, you could produce Higgs, which through what is called the gluon fusion channel. He discussed in detail what is the basis that can be used to describe such a process, in this case for on-shell gluons. And he did a calculation in which he shows that he's starting to get results from that approach, and eventually try to compute the full cross-section for this process. Now, Saul just told us about quarkionic matter and how in this model that they are building, they are trying to incorporate the effects for the equation of state when you take into account this transition region when the density is growing from the nuclear density to very high densities. The importance of the quarks, of course, is growing as the density increases, as the chemical potential increases. So now let me go to the next topic, which I called stars. And here we had contributions from Jose Jimenez, Manuel Mañeiro, Eduardo Fraga, and Igor as well. And so Jose Jimenez told us about how the boundary conditions between quarks and hadrons, the interplay can be helping to taking into account this interplay can help us to better understand the equation of state. In the case of, I can't see you well here from here. What Manuel did was something which is a word of caution, I think. He emphasizes, not only during his talk, but also during his questions, that if we naively assume that magnetic fields within compact objects are very large at the surface, then this has consequences. And one of the consequences, of course, is the deformation of these objects. And so because of that, then it's got to be, calculations here have to be done with care because he cautions that in order to have some magnetic fields of an intensity as high as this, to have consequences, then you would need a larger intensity in the core, but typically these intensities fall down rapidly and a couple of orders of magnitude all the way to the surface. So perhaps just assuming that the field is very intense in the core is not the best case. So this is just an example of how for instance, the mass changes as a function of the radius. Cowan, on the other hand, studied the effect of the delta baryons in magnetars. He has this model that it's been explored for some time, and this is the consequences. Of course, these are the species that populate the density and as a function of baryon density and how they change when you include magnetic fields. And this is an example, of course, that if you assume a large magnetic field for the center of the object, then the drop when you get to the surface of the object, it's not that high. So if that's the case, then perhaps, as Manuel was saying, one should perhaps look for some other effects that may still allow a large magnetic field in the core, but have them drop faster than this. Igor was studying plasma stabilities in the magnetosphere of a magnetar. And so he has this very nice picture where he showed us that this region is not boring at all. It's actually very active, and so it has lots of physics. In particular, it produces gaps which may help to understand the burst of gamma rays that are observed in this kind of coming from these objects. So these are the so-called pulsar gaps. So now let me move forward and let me call these other kind of contributions or group them in what I call the searching for electromagnetic effects in heavy ion collisions. And so here we had contributions from experimental colleagues. So Cesar Bernardes, Daniel Brandenburg, Gang Wang, Sheikh Iqbal, and well, Igor as well in the colloquium. So in the case of Iqbal, he showed us that there is an interplay between the kind of electromagnetic processes that are present in these reactions, and also it is important that when you look for a signal, you get rid of the transported light species to be able to distinguish a signal better. And so he came up with this, well, he showed us that there is this variable, it's called delta V1, where V1 is the directed flow. And what he showed us is that depending on the characteristics of this function, then you could perhaps have a handle on what is the general, the relative contribution from these three processes that are playing a role in these reactions. He mentioned that it is important to have the input from theorists to try to disentangle this. There is another way of searching for these effects. Cesar told us about this, and this is looking at V2. So working from CMS and also looking at V2 of these zeros, he was also able to produce some observables, the V2 distribution as a function of azimuthal angle, as a possible handle to distinguish this, the presence of magnetic fields. The search for the chiral magnetic effect continues, so it's, I believe that this shows character in the experimental community. Even though some of the results may be discouraging or may be thought to be discouraging, this is not being given up, and so more sophisticated analyses are present, and so even though the signal is still consistent with background at high confidence level, the search will continue, and there is also some more tools and techniques that are being developed. Igor presented his, by now, classical calculation of the synchrotron radiation emission in thermomagnetic medium. And so he showed that this could be a very important phenomenon. Of course, the fact that there is a magnetic field present makes V2 to be non-trivial. And he also emphasizes the fact that even though V2 here is negative, of course, this is a region which is not accessible for experiments. So perhaps we should not pay much attention to this, but to look at this trend rather than another one. And so he also not only did it for photons, he did it also for dileptons. And what we may think in terms of the relationship between one and the other is that, well, dileptons are not on-shell photons. So it's not surprising that the dilepton spectrum, in particular as a function of the invariant mass, also shows some effects. I put forward the question of whether or not there are some other channels open for photon production, and I discussed a little bit of what is the possibility if we look at pre-equilibrium to this kind of channel, gluon fusion or splitting. Now, we also had some discussion, very active discussion for low-dimensional systems, Gabriel, Alfredo, and David. And Gabriel presented to us some statistical model for interaction of quasi-particles. What he has in mind is some description of an abelian quantum Hall effect, which is, well, I mean, I'm not an expert, of course, but it left me intrigued. So what he said is that the model presented localized boundary states if n Chern-Simons is different from 0. So he introduced this charge in his model, and so Alfredo did as well. So he's looking for how the Chern-Simons term restores chiral symmetry. And what he says is that the theta parameter acts as a dielectric constant, and that large values of theta restore chiral symmetry. Of course, there is a critical value for the coupling constant where that happens. He is working in the rainbow ladder approximation. So in that sense, of course, this number has to be taken with a grain of salt, but Alfredo is confident that if you use the correct dressing for the vertices and propagators, then the dependence on the gauge parameter can be mitigated. David was discussing also the 2D materials, and in particular, he was discussing the quantum Hall effect. I was also intrigued by the fact that he gets a half-integer quantum Hall effect, but he made an emphasis, or he made a point to say that in order to get it and not to have a 0 result when you sum over two polarizations, you need that the mass also depends on the spin. So I guess that can be possible, and then, well, but still, he says that the origin of this fractional value, it's topological in nature. Then we move to lattice QCD, which is happened today, and so there are very interesting and exciting news from lattice QCD. In particular, for instance, from a simple description of the a way to describe how a magnetic field can be can have certain structure, not to be just a constant, but to depend on the location. One is able to see that the chiral condensate is, depending on the temperature, of course, will not follow the profile of the maximum distribution of the magnetic field, but there will be some regions where the chiral condensate will be more important than just the region where the field is maximum. So also he made a point to mention that lattice QCD with magnetic fields is the first theory that distinguishes clearly a first-order phase transition in QCD at physical masses and physical parameters. So this is interesting news. What is also interesting but intriguing is that it seems that although the chiral magnetic effect signal, as computed by lattice, it seems to be 0, seems to vanish, and so it may be interesting. On the other hand, the chiral separation effect seems to be there and alive. And so he also, Gergo in this case, described to us how you do understand what is the meaning of a system which has an electric field which not just acts as a particle accelerator and then gets rid of all of the charges in the plasma. And so this is the picture. And he also emphasized that there is something still to be done in understanding what is the two pictures that are able to compete in the formalism to do this kind of calculations, because there is a different sign here if you do it a la Weldon instead of a la Schwinger. The difficulty seems to be that in the second case, You first start with the Schwinger propagator, and therefore you're already in the limit when the volume is infinity, and then you take E equals 0, whereas in the way Weldon does it, it's the opposite. So there is room for thought, I believe, in this subject. So let me skip. Of course, all of this information is very interesting. So let me just, to not take much time, because this, of course, is just a summary, as I said. I'm not going into details, but what I like to do is to try to ask the question that perhaps we should be asking ourselves, but this kind of meetings helps to ask again. So where do we stand? And how can we better learn about the nature of these strongly interacting systems when we probe them with these electromagnetic probes, these electromagnetic fields? Sometimes I'm using this Enrique's picture for another purpose. So sometimes I feel like, I think this is Diogenes, right? So I feel like him. You know, after preparing the summary talk, I'm dead. I'm just ready to lay down here on the stairs. And well, what is keeping me is that I want to learn something from you, and also the possibility of caipirinhas at the end of this day. But yeah, perhaps we all feel like this, but of course we should feel like Aristotle and Plato, you see, because we're also asking for very deep questions on the nature of strongly interacting matter. So what is this electromagnetic fields? What are these electromagnetic fields doing to these strongly interacting matter systems that make them behave sometimes in a non-intuitive way? And so one of the, I believe, one of the things that is important from these kind of meetings, and of course from our field, is this crosstalk between theory, experiment, and also some other fields which may sometimes seem to be far away. It's not the case. Condensed matter, heavy ion collisions, stars, there's a crosstalk, and it can be very productive. But I believe, although it's a fertile ground, it is still not there. We are still missing these discussions which take us a bit deeper into see how from one of these fields we can take ideas and propagate them to the other one, and so try to make connections and do our job in a more coherent way. Of course, Lattice QCD provides a guide, and there is lots of results there, so we should keep there and keeping an eye on that. But I believe that perhaps more important is that we need to relate calculations to observables. So far, there is very little work in that direction, and I urge you that you look into that to make this field even more fruitful. So with this, I thank you, and if it's possible to motivate some discussion, it'll be great. So thank you very much.
Thank you very much, Alejandro. So someone wants to say something? Comments? Perspectives? Criticism? Something we can do better? No, we did the best. Okay, so there is something we can do better.
Well, I really just wanted to thank again the organizers, everybody, and in most particularly for organizing this. And I think we have to start planning for something similar in 3 years, 2-3 years, I don't know, so that we know that there is something to do, and there are some people who will be interested to listening to the progress done. So thanks for organizing, and I guess on behalf of everybody, thanks. It was really great.
Thank you. So I also want to thank, so I'll just show you a couple of slides. And just a second. This computer has a problem with my USB stick, apparently. Yeah, can someone lend me the computer? Norberto, ¿cómo lo pongo en full screen? Ah, ya. Ya está. So just some final acknowledgements. I want to thank again our sponsors, ICTP-SAIFR, IAN QCD, Latin American Center of Physics, and also Alejandro mentioned, of course, IFT and the São Paulo State University, who gave us the structure to do that. And I would like to thank the staff of ICTP, here represented by Tiago, who did a great job of making everything work smoothly. Jandira, Humberto, and Gui, they're not here today, but they have been working a lot since months ago. So I'd like to give you a little present. Thank you very much. This is great. Everybody's impressed. And also, I'd like to congratulate a couple of colleagues from our community who recently got prizes. So Alejandro Ayala got the Mexican Physical Society Medal of Scientific Research 2022, and Alfredo Raj got the Michoacán State Prize for Advances in Science in 2022. So let's congratulate the colleagues. And that's all. Thank you all for coming. Hope to see you soon, and maybe in Trento, maybe sooner, a few of you, or in a couple of years. So thank you very much.